Okay, in this example, we're going to be simplifying the expression x squared plus 2x over 3x minus 5. We're going to be also assuming non-zero denominators as we do this. So we're going to have to start by finding a common denominator here. And the denominator with x squared, since it's just a whole value there, is just 1. With that being out of the way, for our common denominator, it needs to take each factor we see in the denominators to the highest power in any one fraction. The second fraction, the denominator is already factored, and the denominator of the first fraction is just 1. So the only thing we really need for our common denominator is just the 3x minus 5, because the 1 is technically already implied. Second step is to balance our common denominator. So we'll have 3x minus 5 underneath both fractions. Top, we originally have the x squared on the first and 2x on the second. The new factor on the bottom of the first fraction is obviously the 3x minus 5. Wasn't there originally, now it is. In the second fraction, there is no change. If you really wanted to put something, you can put a 1 because you're not really changing anything there. But it's not necessary. Now we'll take a second to rewrite as one fraction before simplifying. So x squared 3x minus 5 plus 2x over a common denominator. We'll distribute things out. So we'll have 3x to the third minus 5x squared, then plus our 2x over our common denominator. We have no like terms, so we're done simplifying the numerator. Now all we have to do is see if we can factor and cancel. So I do see that there is a factor of x in all three terms. So I can pull the x out. I do know I can factor this, but based on the last term, I can tell that we won't be able to cancel anything out. However, if you do want to factor, just to be sure, the top would factor as 3x to the third minus 5x squared plus 2. Multiplying our first and last, we would have a positive 6x squared. The combination we would need would be negative 2x and negative 3x, and I messed up my exponents whenever I was doing this quickly. Did them in my head, but not actually on the screen here. So the combination of factors would be the negative 2x and negative 3x. So we go through and write out, break it apart here. So 3x squared minus 2x minus 3x plus 2. Doing the grouping, we would have an x and negative 1, it looks like, for the second grouping. 3x minus 2 is left over, and 3x minus 2 would be left over there too. So over all the factors of the top would be x, and 3x minus 2, and x minus 1 over the 3x minus 5. Now, as you can see, nothing cancels out. I could easily tell that from before just by applying the rational root theorem, which is the theorem with the p's over the q's for the ending coefficient, or the constant term and the leading coefficient. I can tell that since 2 doesn't have any factors of 5 in it, we wouldn't be able to get a factor that would match any of the factors in the bottom from the top. However, that tends to be a little less straightforward for people sometimes applying that way. So you can always factor it and just see from there. But either way, as far as an actual answer choice goes, I think both would probably suffice as far as multiple choice questions and stuff. Okay, in this example, we're going to be simplifying this expression and assuming non-zero denominators. Now, in order to simplify this expression, we're going to kind of have to identify what operations wouldn't need to be performed first. So we have four fractions kind of involved. We have this first fraction, which consists of a top fraction and a bottom fraction, as well as this fraction being added. Now, no matter how complicated things are, this amounts to just following order of operations. Anytime you simplify an expression, it amounts to following order of operations with whatever pieces that you can do, and then just applying algebraic properties from there. Even what I call the revenge problem that I allow my students to create, assuming everyone does their work, which should be up on the next screen. But with that being said, going through, here is where we have to start for this. So each of these three things in parentheses is a separate fraction. Treat like a separate number. And where we would start with them, we would start dealing with the stuff in parentheses, but we can't simplify anything in the individual fractions themselves. There are no exponents that we can deal with. So we're going to start with multiplication and division, and the part that's connected by multiplication and division are these two fractions in the red parentheses. The blue fraction, the one that's in blue parentheses, is separated from the others by addition and subtraction, so that will come last. Since the ones in red are connected by division, we'll do keep, change, flip. Keep the first fraction, change it to multiplication, and flip the second one. I'll go ahead and bring down my blue one, but keep in mind this is separated by addition and subtraction. So as I focus on this multiplication problem, because I'm still simplifying this part first, order of operations says multiplication first. As I focus on this, I'm going to be ignoring the other fraction here and just reducing it like we normally would. There's a factor of x minus 1 on top and bottom, so they can cancel out. No, we cannot cancel out this one because it's separated by addition, so we cannot do that. And we can reduce the factor of 2 here, leaving us with 2 plus 3 over x minus 1. Now we're ready to continue with the addition part. So we need a common denominator, and x minus 1 is really the only thing on the denominator. Technically, 1 is for the 2, but x minus 1 will be our common denominator because x minus 1 times 1 is still x minus 1. So I'm going to place my x minus 1 underneath each fraction, and then seek to balance out my common denominator, which the first fraction will need to multiply by x minus 1. The second fraction already has the x minus 1 and doesn't need anything else. We'll go ahead and write it as one fraction over my common denominator. Distribute, giving us 2x minus 2 plus 3 over my x minus 1. Combining like terms, 2x plus 1 over x minus 1. And that's actually all we can do. We can try to factor and cancel, but it doesn't actually factor. So that's the final answer. So in this video, or in this example, we're going to be simplifying this expression and assuming non-zero denominators. And this is just a rational expression, no matter how complex it gets. Anytime you simplify rational expressions, you follow order of operations. Please excuse my dear Aunt Sally. So there's a couple things going on as we look at it. We have this giant fraction bar, which means the things on top are in a set of implied parentheses. We also have technically parentheses on the bottom of each fractions, which won't really help in this situation. So I think that's really the only determining set of parentheses that's helpful for this situation to place it and make them visible as we go through this. So as we go through doing order of operations, we would hit up parentheses first. Now, most of the parentheses, like I said, that are implied here don't really affect the problem, but this blue set of parentheses does. We can actually do something with this set of parentheses. We can actually combine those into a single fraction, and that's what we're going to do. So to do that, I will go ahead and find the common denominator between the two fractions, which is x and x minus 1, it looks like. So I'm going to focus on the top there. Write my two fractions out with my common denominator under each. On top, they originally have 1 and 1. The new piece on the first fraction is x minus 1. The new piece on the second fraction is just the x. And of course, we have the all over x squared minus 1. Don't want to forget about them, because if I don't write it down now, I may forget about it entirely. I'll next write things as one fraction, and since it's multiplying by 1, and there's not two terms over here, I'm going to go ahead and actually do this multiplication this time. 1 times x minus 1 is just x minus 1, plus my 1x, or just x, from the other fraction, over my common denominator of x times x minus 1, over my x squared minus 1. You'll notice with that one, I'm trying to keep my my fraction bars the correct length and everything. This way, whenever I do the keep, change, flips and multiply them by the reciprocals, I know which parts are being flipped and which parts stay the same. That is important and does affect the problem as you go through. If I continue going through this, combining like terms, we have x and x, which makes 2x minus 1 over the common denominator of x times x minus 1, which is over x squared minus 1. Now we are ready to deal with this fraction bar here in the middle. We'll do keep, change, flip. If you're curious of how that will work, this is the first fraction on top. The second fraction is technically over 1. So when I do keep, change, flip, it will look something like this. So 2x minus 1 over the common denominator that we had. Change its multiplication and flip the second fraction. Now our process is to factor everything and to try to cancel, because this is now a multiplication problem. I can factor stuff. It doesn't really look like anything is going to cancel. 2x minus 1 can't be factored. X and x minus 1 is already factored. But x squared minus 1 can factor into x plus 1 and x minus 1. The 1 on top doesn't really change. So it looks like this really doesn't cancel out very nicely. Instead, we just end up with 2x minus 1 on top. And on the bottom, we have x and x plus 1 and an x minus 1 squared. Doesn't really cancel out nicely, but it is what it is. Sometimes that happens with these problems, especially as you go to other courses, and these are used in the middle of other things, such as calculus and doing derivatives and integration and stuff. Okay, so this is just a little addendum to this particular example. So I did it in one method, but there's another common method with dealing with these fractions on top of fractions, which I have yet to mention. Sometimes this is easier, sometimes it is harder. It just depends on the situation as for what might be the better option. But to deal with this fraction on top of a fraction, I can simply just find the common denominator between these two fractions and multiply by x minus 1, which is the common denominator between the two fractions, on top and bottom of the larger fraction. By the larger fraction, I'm referring to this bar here. And what that will do is it will end up allowing this x minus 1 and this x minus 1 to cancel, and this x minus 1 and this x minus 1 to cancel as well, leaving us with just 4 over 2 plus 3 over x minus 1. It's a handy trick, which doesn't violate any algebra properties because we're technically multiplying that first fraction just by 1, that larger fraction just by 1 because it's x minus 1 over x minus 1. And it allows us to get to this in a nice and efficient manner. Sometimes the strategy can make some problems be even more efficient. Sometimes it can make it longer. It just depends on the situation. This particular problem, I could have also done the same thing. I could have chosen to focus on multiplying the top and bottom of the larger fraction by the common denominator that I had found earlier. So I could have multiplied it by x and x minus 1 on top and bottom of the fraction as a whole, which would have resulted in the same result, but in a different way. It would have changed it because I would have been distributing this to each of the individual fractions, canceling out, leaving me with x minus 1 for that first piece, the x being the thing that canceled out, and then plus, when I multiplied the x times x minus 1 by this, it's going to give me just the x, because the x minus 1 factor cancels out. Over on the denominator, I would have the x squared minus 1 times the x and x minus 1, effectively resulting in skipping a large portion of this work. So sometimes the strategy can be very effective, and sometimes it's not as easy to implement. It just depends on the situation that you're in. But either way, you can get the correct answer. But knowing exactly what to multiply depending on the complexity of the fraction, doing it this way can be a little challenging at times. Just a little. So I mentioned my revenge problem. It's a problem that I allow my students to create if all of them do their work for a certain group of topics. This is the problem that I had last year. And as complex as it looks, it starts off just the same way as all the other ones. Figure out where the parentheses are and just try to figure out where you would start for order of operations. So you can see I have it kind of broken down. The first round I went through and just verified where they had intended the parentheses, because when they hand wrote it, it wasn't very clear as to where those parentheses were. And then I just started breaking it down, knowing what I needed to do, keep, change, flip, and just broke it down further and further and further, and factored with whatever we could possibly factor. And as you can see, this is the result that I had. Some of these numbers got pretty massive, and I did try to break down everything that we could. Yeah, this is, and you can see I can kind of left some of them, and you can see like 3 to the 14th and 19 to the 7th power and stuff, just because those were more practical, and it allowed me to factor out common monomials a little bit easier than some of the other things. You can see that at the bottom of some of these, I have a large number in parentheses with pi and stuff. So those were the coefficients beside the x to the ridiculously high powers. But yeah, that's the revenge problem. Is it right? Well, I have no clue. But if you want to find out for sure, go ahead and try.